Good morning everyone. In this video I'll be discussing about event synchronization. We'll be looking at synchronous and asynchronous communication within processes for the inter-process communication, and then we'll be seeing different combinations of send and receive operations in terms of synchronous and asynchronous. I will also be discussing about event diagrams, okay, and then timeouts and deadlocks. So processes involved in inter-process communication actually execute independently. Okay, so we have already seen process 1 is trying to communicate with process 2, but they are actually running on different machines. Okay, so both processes do not know what is happening on the other side. Okay, so if you are issuing a send or a receive, okay, so or even a connect or whatever it is, whatever the operation, you don't know what the other process is actually doing. Okay, so then IPC inter-process communication somehow requires this sort of these two processes should synchronize their operations somehow or other. Okay, so if one side sends, then the other side should receive. Okay, it should be in the receive state. Okay, it should be in issuing that receive operation, and it should be receiving until all data has been sent. All data that has been sent is actually received at the second process. Okay, so this sort of synchronization is actually necessary. Okay. Ideally, send operation starts before receive operation commences, but who ensures that? Okay, so somehow a protocol should be ensuring that one. Okay, so in practice, actually, this sort of synchronization between processes actually requires system support. Okay, so we'll be looking at this event synchronization in detail, how to deal with this one. So there are two different types of communication. Okay, one is synchronous communication, another one is asynchronous communication in inter-process communication is concerned. So the first one is synchronous communication. So here the IPC operation actually may provide this synchronization which is actually required through blocking. Okay, so a blocking operation issued by a process will block further processing of the okay, of that particular process until the operation is actually fulfilled. For example, okay, so let's go with the browser and then the web server example which we have discussed earlier. Okay, the browser process issues a blocking connect operation. So it issues a blocking connect operation, so which will actually block that process until you actually get an acknowledgement from the server that the connection is actually accepted. Okay, this is one example. So here the synchronization is actually provided through blocking. Okay, so the IPC facilitates that. Okay, so basically both the blocking and unblocking are actually initiated by this sort of IPC facility. Okay, so once this sort of you initiated a blocking connect, okay, so operation, the web browser, so then the server actually accepts this connection, and then it actually acknowledges. Okay, once you receive the acknowledgement, okay, you basically do the unblocking, and both this blocking and unblocking are actually initiated by the IPC facility. Okay, but there is a problem here, okay, with this sort of blocking, okay, for the synchronization. If the operation for which you have actually blocked cannot be fulfilled, the process ends up in indefinite blocking. Okay, to go with the same example, you initiated the connection, somehow the connection is lost. Okay, so due to network error or something. Okay, so then this process which actually the browser process which actually initiated this connection operation, okay, issued this connection operation, is left in this sort of indefinite blocking. Intervening measures are to be taken. So there are several approaches for them, which we will be discussing later. So the other type of synchronization is achieved through asynchronous or non-blocking. Okay, so these IPC operations in that sense can be asynchronous or non-blocking. An asynchronous operation issued by a process will not block further processing of the process. So for the blocking, we have discussed, a process is executing, there is a blocking operation issued, so the process itself is stopped. It cannot do anything else. With asynchronous or non-blocking, okay, operation, you don't have to do that one. The process will issue that operation, asynchronous operation, and it will continue. So the process is free to proceed with its processing. It will continue with its remaining processing. The process may optionally be notified by the system or IPC facility with the operation being fulfilled. So if you have issued an operation, you continue with the execution of that process, okay, because that is an asynchronous operation call, okay, issued. So once this operation is actually finished, the system may actually notify this executing process that that operation is actually fulfilled. Okay, so the send operation. So let's look at the other end. Okay, the send operation. Once the results are sent back to this sort of browser from the server, the send operation issued by the web server can be non-blocking. So that means like it sent the data, sent the response, and immediately it continues with its execution. Okay, and then like proceed with processing other claims. So in that sense, like the send operation there is actually asynchronous at the web server. So these are the synchronous and asynchronous communications, okay, which are actually required for this sort of event synchronization is concerned. But remember that it is actually the programmer's responsibility to decide whether the operation is blocking or non-blocking. For example, like the program has developed in such a way that the browser issues a non-blocking receive operation. Okay, so the browser this side, okay, so it issued a non-blocking receive operation, which it is actually expecting the assumption is that it is actually expecting the response from the server immediately, and all the data is immediately received. Okay, but what happens if it is non-blocking and you have not received the complete data? So that the browser may actually display invalid data, or in certain cases it may even generate errors. Okay, so it is the programmer's responsibility to see like which of the operations should be blocking and which of the operations should be non-blocking. So since okay, so we have already discussed about different operations in inter-process communication regarding those connection. Okay, so disconnect and then like send and receive. Out of which like send and receive are like pretty much used quite a lot. Okay, in inter-process communication. So let us try to see different combinations of these send and receive operations, both in terms of synchronous and asynchronous. Okay, the first one could be like synchronous send and synchronous receive. That means both are blocking. Okay, see here. The process one actually, okay, is initiating, okay, is issuing a blocking send operation. Okay, so the blocking send actually stops, and then like process 2 is actually issuing a blocking receive operation. Both are actually blocking. Okay, it may, since both the processes don't know like what is happening at the other end. Okay, so the blocking receive operation by the process 2 may be initiated a little bit early. Okay, these diagrams are called event diagrams. I will discuss about event diagrams in when one of the coming slide. Okay, so this is this axis is the time axis. So actually, like the process 2 is actually executing, and it actually has issued a blocking receive. Okay, and it is actually waiting for some data to be received. Okay, from process 1 actually. In the meanwhile, like the process 1 also has issued a blocking send, okay, send operation. So that means like data is actually sent. Okay, so that means like data will eventually reach here, and then like then this receive operation will receive all the data. Since it has received the data, so then an acknowledgement, okay, can be sent, okay, that the data is actually received, and this acknowledgement is actually provided by the IPC facility. And then like both processes can continue with their further execution. This sort of blocking send and receive may be required if the application logic of both the processes actually require that the data sent must be received before further processing. Okay, so this is where like synchronous send and synchronous receive may be warranted. Now let us look at the second type. Okay, so the sending is actually a synchronous type. Okay, that is non-blocking, and the receiving is actually a synchronous thing. Okay, again we go with the same thing. So we have this sort of blocking receive is issued by this sort of process 2. Okay, so that means like it is actually waiting, but process 1 actually issues a non-blocking send. Okay, so process 1 issued the non-blocking send. That means like the data is actually sent. Okay, and then like process 2 basically receives the data. Okay, and then like once it is done, then basically like the process continues execution with process 2. Okay, but there is a catch here in this part, in this sort of communication. There is no guarantee that the data is delivered to process 2 from process 1. Okay, So think about the situation, like the send operation is actually issued before the receive operation is actually issued. So example, like say for example, since process 1 and process 2 don't know about what is happening at the other end, okay, so the idea is like the blocking receive has actually started here. Assume in terms of the time, okay, even before the blocking receive, okay, operation is issued in process 2, assume like before that one itself, at process 1, sometime here, if you assume like say for example this non-blocking send has been initiated, okay, say for example here, then it's a problem. Non-blocking sent is sent, and then like the data is actually sent. There is no process waiting for it to be received, okay, and then the data is actually lost, okay. So in such a cases, okay, so IPC facility, so inter-process communication facility, whatever you are providing, must, okay, so it must retain this prematurely sent data somehow, okay. In terms of the implementation, it may have to take care of that one, okay. That's about asynchronous send and synchronous receive. Now let us look at the third approach. Both, okay, actually here you are actually synchronous send, so blocking send you are issuing, okay, and the receiving is asynchronous receive, so non-blocking receive. Here the outcome actually depends on the implementation of the inter-process communication facility, okay. So there appears three different scenarios for that one, okay. Let's look at the first scenario. So basically, like here, the process 1 is basically giving this blocking send operation, issuing the blocking send operation, okay, and process 2 actually has issued a non-blocking, okay, receive operation, okay. So the blocking send has been issued, so the data is actually sent, okay, and say for example, after the data is sent, like immediately, like you have received this, I mean, non-blocking receive has been issued, so the data is completely received by this process. Since it is received, it can basically send this sort of transparent acknowledgement, okay, provided by this sort of IPC facility. Then process 1 continues execution, okay. So here the data is properly delivered, okay, so no issues, no problem, okay. So with this synchronous send and asynchronous receive in scenario 1. Say for example, if the implementation is like this. Let's look at scenario 2. The scenario 2 is a little bit problematic. You have issued a blocking send, okay, operation, and non-blocking receive has been issued before you actually sent, you issued this sort of blocking send operation. So that means like the data is actually sent here. Before that, sometime earlier, like non-blocking receive has already been initiated, and since it has not received any data, it immediately returned because it's an asynchronous receive, non-blocking. So no data is read. Actually, since no data is read by any process, okay, so the process is no more waiting for that receive, okay. So the data is actually lost, okay. So nobody else is actually informing process 1 what is happening, okay, whether it has received the data or not. So then process 1 actually ends up with this sort of indefinite blocking, okay. So in such scenarios, it is actually the responsibility of the receiving process to ascertain that the data is indeed received by it, okay. Process 2 has to inform back that it has actually received the data, okay, or else like the process 1 is actually ending up in this sort of indefinite blocking. So there are several solutions for that one, okay. So one of them is like this polling. So polling is like, say for example, you issued a non-blocking receive and you immediately return because there is nothing received. But you can actually issue non-blocking receives, okay, multiple times. So you can actually repeat in a polling loop, okay, in a loop until you actually receive the data. That means like this non-blocking receive is actually issued several times, okay. Eventually you will receive the data because the send is received, okay, and you receive the data and then acknowledgement is sent back so that process 1 can continue. So that's about polling, okay. So continuously having a loop to issue this sort of receive operation. That's about scenario 2. There can be a third scenario also possible, okay. So in this case, like say for example, okay, so a non-blocking receive is issued, okay, but it is not being repeated, so there is no polling is happening, okay. But then like a blocking send has been issued at process 1, which actually sends the data. Now the IPC facility actually knows that the data is actually received, even though this process is not waiting. So the IPC facility can actually notify this sort of process 2 that the data has been received, okay. And then like, okay, that data is actually collected by process 2, and then like you can send an transparent acknowledgement again sent back to process 1, okay, by this sort of IPC facility. In this way, again, like process 1 will not end up with non-blocking, okay. But in this case, like process 2 must implement some sort of listeners or event handler that is actually invoked by this sort of IPC facility. So the process has to give some sort of listener or event handler, okay. Or else how else like the IPC facility will be communicating with this one, okay, or notify about the data being arrived, okay. So this is about the scenario C for synchronous send and asynchronous receive. The fourth type is like both of them are asynchronous, okay. So you have this sort of non-blocking send and you have this sort of non-blocking receive issue, okay, and it is returned immediately. So earlier, like in scenario 3 of for the case 3, okay, so basically like synchronous send and asynchronous receive, we have already seen what can be done. So for example, like once the data is actually received here, the process may be notified of the arrival of the data by the IPC, okay. Just now we have seen, so by using a listener or event handler, okay. That's about this sort of fourth approach, okay, of asynchronous send and asynchronous receive. So I quickly said like these diagrams are actually called the event diagrams, okay. So the event diagrams are actually put like this one. So basically like if there is process, the sort of dark line actually means like the process A is actually executing, okay. Here it is actually executing. When they are dotted lines, so that means like it is actually blocked, okay. So similarly like here it is process B is executing, okay, process B, and then like it is actually blocked here, okay. And event diagrams you actually use to basically show different protocols, okay. Say for example in the earlier like all these sort of four different types of send and receive with asynchronous and synchronous, okay, we have actually seen, okay. But assume like there can be a protocol which is defined here. Here you can actually say like say for example process A, okay, so initially it is running, process B is also initially running, and then like say for example process B initiated a receive operation, okay, issued a receive operation here, okay, and then like it is blocking, okay, so it is synchronous receive, so that means like it is waiting for the data. Whereas like process A can initiate like an asynchronous send. That means like send is immediately sent, and then like it has issued a synchronous receive. Okay, so that means like a blocking receive has been issued. See, initially it has issued an non-blocking send. Okay, the data is actually sent, and the like, process is continuing. Then it is has issued a blocking receive. So it is actually receiving. It is actually blocked for receiving the response. So for at the other end, since you already have this sort of blocking receive, you receive the data here, which is actually the request. You actually process the request, okay, and immediately you can issue a non-blocking send of this sort of response, okay. So the response is immediately sent, and the process continued, and then like it may issue like another blocking receive to receive the next request, okay. So here at this process A case, okay, so the response is actually received here, okay, and then like the process continues execution, it will be processing the response, okay, and again like it can actually send another asynchronous send for the next request, okay, and then may issue another synchronous receive for the response from it. So this way like this sort of request and responses are actually continued. So this is how like a protocol can be defined, okay, and then like you can actually show it with an event diagram. So here I have talked about synchronous send and then like asynchronous receive, okay, happening at both the processes, okay. So that means like for one request and then like one response to happen, you have a pair of synchronous send and asynchronous receives happening at both the processes, okay. So that's about that's how like you can actually define a protocol with this sort of blocked and non-blocked send and receive. Okay, so that's how like you actually synchronize between the two processes. Okay, so this is all has to be agreed within a protocol, and everybody has to follow these protocols. All processes have to follow these protocols. So we have seen like indefinite blocking. Indefinite blocking is always a problem. Okay, because like you are putting this sort of blocking send or receive. Okay, okay, or even those other operations, the connect and okay, disconnect as well. Okay, so basically like you have this sort of blocking operations. The blocking operations may end up with some sort of indefinite blocking cases. Okay, we have seen already several cases. Okay, so it is generally unacceptable for a requesting process to actually hang indefinitely. Okay, so for example, like these connect and receive operations can result in indefinite blocking. I already talked about it. Say for example, you issued a blocking connect request. Okay, and the connect request should be initiated to a server. Okay, and assume like due to some network connection failure or something. Okay, so the network the connection acceptance acknowledgement you have not received back. Okay, so this process is actually blocked, it is indefinitely waiting for it. Okay, so that's a problem. So this indefinite blocking can be avoided by using timeouts. Okay, timeouts is like, say for example, you can actually set some maximum time period for blocking. Assume like you issued a connect, okay, connect request, okay, connect operation, okay, to a server, and you can put a timeout of something like 30 seconds. After 30 seconds you think like there is some error, and then like you continue the process again. And if you want to initiate another connect, issue another connect operation after that 30 seconds. Okay, in that way like the process one is not completely blocked always. Okay, so that is one way of avoiding indefinite block using this sort of timeouts. Alternatively, what you can do is like, say for example, okay, say if there is a scope for the process to be ending in indefinite blocking, okay, because of that implementation, okay, the program may actually spawn a child process or a thread to issue this sort of blocking operation. Okay, so here in this case, like the process is continuing, okay, the main thread actually has issued a new thread for issuing this sort of blocking inter-process communication operation. So in that sense, like the process, the thread, or like this child process is actually blocked here. Okay, once that blocking operation is actually finished, the thread is actually unblocked. Okay, and it will continue with the execution, and then like you may come back to this sort of main thread. But the issue is like during this time, the main thread continues with other processing. So the non-blocking, I mean like this indefinite blocking is actually avoided. Even if the indefinite blocking happens, it is the thread which is indefinitely blocked, but not the main thread. Okay. So the importance of this one is like it always depends on how the IPC is actually implemented. Say for example, if you have implementations for only blocking operations for both send and receive, okay, the IPC facility has actually provided you. But like say for example, you want to achieve this sort of asynchronous operations, how you will actually do? Okay, then it is up to the programmer's responsibility. Okay, so the programmer may actually decide like, okay, so I only have got this sort of blocking send or receive, okay, but I want to achieve asynchronous thing. Then it is up to the programmer, he can actually initiate this sort of child process or threads, so that like your implementation of that send and receive is blocking, so the thread is actually blocked, but your main thread is still continuing. So as far as this programmer's implementation is concerned, he has achieved an asynchronous send and receive in that case. Okay, so it is the programmer's responsibilities there. This is about indefinite blocking. The indefinite blocking may also be caused by a deadlock. Okay, so deadlocks are much bigger problems actually. Okay, so these blocking operations are actually issued in wrong sequence. So that means like somehow these processes have not understood the protocol properly, and then like so this is a much bigger problem. And then like so the corrections have to happen. Okay, so they are not following the protocol properly. Okay, there are errors in that one, and deadlock should always be avoided. Okay, so very simple example can be like, say for example, process 1 actually have issued a receive from process 2 operation, and process 2 at the same time, sometime later, it has actually issued a receive from process 1. So that means like both these processes are waiting for something to be received. Okay, and both are blocking here. So that means like both have ended up with indefinite blocking, and this is a perfect deadlock situation. So that means like the protocol is neither not properly defined or like they have not properly implemented the protocol. Okay, so this is about the deadlocks. The deadlocks basically like will continue like this one. Okay, I mean like again you can have a timeout so that like both the processes get killed, but then again like if they follow the same protocol, then they will end up with the same sort of scenario, or else like these processes will be continuing even if you don't have the timeouts put there. Okay, so they will be continuing forever until like these processes are killed by this sort of operating system. That's about deadlocks. So regarding the references are concerned, okay, so we are still in chapter 2 of the our primary reference book. So distributed computing principles and applications by ML Layer. Thank you for your attention.